Okay, let's dive right into this. When you pick up Griffith's electrodynamics, you're not just opening another textbook. Nope, this is basically the rulebook for a massive and visible part of our universe. But before we can even get to the famous Maxwell's equations, Chapter 1 gives us the language, the alphabet we need to even read those rules. And that's exactly what we're going to crack open today.
So, before we even write down a single equation or draw a single vector, we have to ask the most important question of all. Kyon, why? Why does this whole chapter even exist? Why do we need all this, complicated vector calculus? Well, it's because we need this new language to answer one huge, fundamental question that drives everything else in electrodynamics.
And this is it. This is the whole ballgame. As Griffiths himself puts it, this is the fundamental problem that any theory of electromagnetism has to solve. I've got some charges over here, the sources. You've got a single charge way over there, the test charge. How in the world did they talk to each other across totally empty space? And here's the thing. The force that your charge feels, it isn't just a simple number. It's not just how much force it feels. It's also in which direction, right? A simple number, a scalar, like temperature, just can't capture that information. We need a language that has both of those things, magnitude and direction, baked right into its DNA. And that language, you guessed it, is the language of vectors. These are the basic nouns of electrodynamics. But for a physicist, we need to ask, what is a vector really? I mean, on a much, much deeper level than just an arrow with a length.
Now, this is the definition we all learned, right? And it's fine. It works. Displacement, force, yep, they have a length and a direction. But what's so cool is that Griffiths pretty much tells us, this definition isn't quite good enough for what we're going to do.
Okay, this is such a brilliant question from the book. I love this. Just think about it for a second. This fruit basket, it has 3 components, right? The number of pears, apples, and bananas. And you can add 2 fruit baskets together component by component, just like you add vectors. So, is it a vector? It just feels wrong, but why? And here is the real physicist's answer. It's not a vector because if you were to physically rotate your coordinate system, your x, y, and z axes, the number of apples and pears and bananas in the barrel doesn't change. But the components of a true vector, like a displacement vector, would change in a very specific, predictable geometric way. A real vector is fundamentally tied to the geometry of space itself.
So the whole point comes down to this quote. For a physicist, what really makes a vector isn't just that it's an arrow. It's that it obeys a very specific set of transformation rules when you change your point of view. That is its true identity.
Okay, so we've got our nouns, these things we call vectors. Now we need the verbs. We need to answer the kaise. How do these vector fields actually change as you move from one point in space to another? To describe all this change, we're going to need a master tool.
And here it is, the del operator. It looks like a little upside-down triangle, and trust me, this thing is the Swiss Army knife of vector calculus. Griffiths calls it a marvelous piece of notational simplification, and he's not kidding. This one single symbol is going to let us describe all the different ways a field can possibly change in space.
Say this del operator can act on fields in 3 fundamental ways. It can give us the gradient, the divergence, and the curl. You can think of these as the 3 main verbs we need to master to describe any field anywhere. So let's build a little intuition for each one.
The gradient is the easiest one. If you're standing on a hill, the gradient just points in the direction of the steepest climb. It answers the question, "Sabse teez chadhai kahan hai?" The divergence, on the other hand, measures how much a field is spreading out from a point. Think of a water faucet. Water is flowing out, it's a source, so it has positive divergence. Now think of the drain in your sink. Water flows in, it's a sink, so it has negative divergence.
And this idea leads us to the super powerful divergence theorem. All it's really saying is that the total amount of stuff flowing out of a closed surface, like a box, is exactly equal to the sum of all the little sources you have inside that box. I mean, it makes sense, right? Whatever comes out must have come from somewhere inside. It's a really profound statement about conservation.
And what's really beautiful is that this isn't some weird one-off trick for divergence. It's a massive, unifying idea in all of calculus. The integral of some kind of derivative over a whole region is simply equal to the value of the original function at the edges, at the boundary. It's just a stunningly simple and powerful concept.
All right, let's get to our third and final operation, the curl. If divergence was all about sources, curl is all about swirls. Imagine you drop a tiny little paddle wheel into a flowing river. If the current makes that little wheel spin, then the field has a curl at that point.
It's basically answering the question, how much is the field rotating or circulating right at this spot? So, we have our nouns, the vectors, we have our verbs, the divergence and the curl. Why did we do all of this work? Well, this is the big top here, the so what moment. It all comes together in one of the most powerful and honestly beautiful theorems in all of physics.
Let's just be crystal clear on this. The divergence of a field tells you everything you need to know about its sources, where the field lines begin and where they end. The curl of a field tells you everything you need to know about its swirls, how it circulates and rotates. Sources and swirls. That's it. That's the whole story.
And here it is. The Helmholtz theorem makes an absolutely incredible claim. It says that if you can tell me these two pieces of information everywhere in space, if you know all the sources, which is the divergence, and you know all the swirls, which is the curl,
then you know the field. Period. That's it. You have completely and uniquely determined the vector field itself. There is nothing else you need to know about it. It's a mathematical guarantee. This is the master key to everything that follows.
Just let that sink in for a second. This is why we spent a whole chapter learning these tools. Because if we can just figure out the divergence and the curl of the electric and magnetic fields, then we will know everything there is to know about them.
And that, right there, leaves us with the final, perfect question. This is the question that connects all of this math from Chapter 1 to the actual real-world physics of Chapter 2 and beyond. What are the sources of the electric and magnetic fields? And what are their swirls? The answer to that? Well, that's Maxwell's equations. And that's a story for our next explainer.